Welcome to NMartech. Rectifier circuits. These are used in power electronics to convert alternating current to direct current to be used by DC loads. This is possible due to the presence of certain components in such circuits. These components are diodes or thyristors. They do the main rectification. Other components like transformers, capacitors, resistors etc. perform secondary, although vital roles in the rectifier circuits. We have mainly two types of rectifier circuits: the half-wave rectifier circuits, and the full-wave rectifier circuits. There are other subdivisions under the full-wave rectification, which are the center-tapped and bridge rectifiers. They all perform the same task but with some uniqueness. Let us look at the half-wave rectifier circuit. Here, the sinusoidal waveform of the AC input voltage is modified after current flows past the rectifier components, which is the diode, as seen on oscilloscopes. In half-wave rectification, only the positive half-cycle of the sine wave flows through the rectifying part of the circuit, while the negative half-cycles is attenuated. This means that current flows through the output part of the rectifier only during the positive half-cycles of the input voltage. During the negative half-cycles, there is no voltage at the rectifier output till another positive half-cycle of the input voltage waveform reaches again. Here, output voltage from the diode rectifier is usually pulsating in nature. The pulsation is at intervals determined by the frequency of the input voltage. After rectification, the AC nature of the input voltage has been altered. The aim is to achieve a form of electricity, likened to that produced by batteries. Now let us look at the full-wave rectifiers. This is a full-wave bridge rectifier. The rectification here is also done by diodes. Here, instead of a single diode, two pairs of diodes are connected to create two pairs of terminals. One pair, as input for the AC supply voltage. The other pair, as output terminals of rectified voltage. In all, 4 diodes are used here. The aim here is to assign 2 diodes each for one half-cycle, and the other 2 for the next half-cycle. Here, in the positive half-cycles, A1 and A3 are active, while B1 and B2 are inactive. In the negative half-cycles, B1 and B2 are active, while A1 and A2 are inactive. With this, provision has been made for current flow through the output of the rectifier during both positive and negative half-cycles of the input voltage. This is unlike the half-wave, and a major advantage of full-wave over half-wave. Looking at the diagram, we can observe that 1. Current flows through the rectifier during both positive and negative half-cycles. 2. Just after rectification, frequency of the output rectified voltage is 2 times frequency of the input AC voltage. 3. The waveform still has some features of the AC waveform. We are still talking about frequency after rectification. But we have to remember that the frequency of a DC voltage must be 0. So, number 2 and number 3 observation implies that this rectified voltage is actually not suitable for DC use. Now, let us observe this third diagram. For both half and full wave, 2 more stages has been added. 1. Filtration and 2. Regulation. Filtration means eliminating all features of AC waveform from the rectified voltage. Here, this visible feature of AC waveform is called ripples. After this stage, it is seen that the waveform is a bit more smoothened. Our aim is a straight line, which is the waveform of a DC voltage source, as seen on batteries. This filtration is done by connecting a capacitor of high capacitance across the rectified voltage. The more effective the filtration, the smoother the waveform. A smoother waveform is usually achieved after filtering a full wave rectified voltage, then in a half wave rectified voltage. This is another advantage of full wave over half wave. The second additional stage is regulation. Every designer has a desired output rating. This value is meant to be steady. For a charger circuit aimed to produce 12 volts DC, at every point in time, within the rated range of input voltage, 12 volts must be present at the output of the rectifier circuit. There is no ideal circuit, and because of this, there are often fluctuations in the output of filtered and/or rectifier circuits. For this reason, regulation is employed to maintain a steady output voltage value. This regulation is achieved by an integrated circuit. They contain components like the Zener diode, capacitor, etc. This regulator circuitry contains component that does further filtration on the output voltage. Because of this, after the regulation stage, a perfect DC voltage is achieved. Thanks for watching. Remember to click your subscribe button.